Hi, good morning. I hope that this video will give you more insights about I will say, the three chapters that we have on exam one. First, I want to give a note here, and that is when the question is gonna say find the magnitude of the electric field at a point P. One of the things that I want to say here, if the electric field expression or magnitude, like it depends, like sometimes you might have this question like find the expression, or like sometimes is gonna be magnitude, then like calculate a value, a numerical value. Then if the electric field expression or magnitude changes from one region to another, then you need to specify and pay attention. Say, okay, maybe I want to divide regions. One of them is R less than R, which are maybe, let's say it's a spherical distribution. Then maybe, okay, R less than R is going to have one expression or one value. And like R greater than R is going to be another expression. Just here, I want you to pay attention to this, because the question will not tell you that there are differences. You need to understand this. And I'm maybe like my, the example that I'm gonna do now is gonna clarify this for you. The other thing that I want to say something about is pay attention when there is an expression asking about a conducting, let's say, sphere, just pay attention for the difference between a conducting sphere and a non-conducting sphere. Now, conducting means the charge. Non-conducting sphere, like sometimes also we call it insulating. Now, for conducting, of course, you know that there will be no charge inside. Then the charge is going to be, I will say, concentrated at the surface. Versus non-conducting or sphere or insulating, the charge can be actually uniformly distributed throughout the whole volume. Now, the expression, the one that I want to maybe discuss with you here, it is the electric field of a uniformly charged spherical shell, and I will say of radius r, and it has charge that is uppercase Q. Then this is really what I am looking for. Let's say, and maybe some of you wanna maybe know like what is looking like. Then maybe like I have a basketball, all right, and it is charged with a charge Q, and it has a radius r. All right. Now, okay, I will say here I don't want to have let's say inner and outer an outer radius. It's just like here it's considered to be very very thin, and I'm gonna assume also it has a positive charge Q. All right, distributed uniformly over its surface. It has a radius r, average radius r, and the charge is uniformly distributed. Here, there is there are two regions. One of them when r is less than the radius, and number two when or where r greater than r. I will use Gauss's law. Then I will say my Gaussian surface by purposes of symmetry is going to be spherical shell, spherical sphere of radius r. And I will have two here, like these spheres. The first one, I'm going to use S1 when r is less than r, and I'm going to use another surface R2 that has, of course, a radius of r, and that is when r is greater than r. Now, let's start with the first one. Then I have that spherical shell here, which has that uniform distribution, and it has a radius r, and my Gaussian surface is going to be this green one here, which I'm going to call this one S1, and it has a radius lowercase r. And of course, Gauss's law over surface 1 is going to be E dot dA equals Q enclosed divided by epsilon 0. Then I am going to look at like how much charge I have inside that Gaussian surface. And just maybe like sometimes you're gonna look at the expression and then you're gonna say, okay, I'm gonna work on the left-hand side. Sometimes the problem is gonna be like very simplified when you're gonna look into your right-hand side. How much charge is enclosed by this S1? Nothing, right? Then here I'm gonna have 0 for a Q, okay, enclosed. Let me write this, enclosed. And therefore E equal 0. And then I don't have any electric field, okay, inside, that spherical shell. Now for number 2 here, again, I'm gonna have the same spherical shell, all right, and it has an average radius r. It is uniformly, all right, positive charge, all right. My surface, okay, Gaussian surface is gonna be, of course, a spherical shell. This is S2. Okay, and now the first thing I will do here, okay, then I'm gonna talk now about the region where r is greater than the radius. Okay, then this one here, the green surface, the green sphere, has r as a radius. The first thing I need maybe to, like the steps for Gauss's law. First, determine the direction of the electric field. And it's very clear that, okay, let's assume my point P is here. All right, then I know that my field will be radially outward. Then it is radially outwards. The second thing is determine the direction of the vector A, which is the area vector. Remember, the area vector always, it is perpendicular to the surface. Then therefore, is going to be, this is the direction. From these two, I can find theta between E and dA, which is, in my case here, it is 0. And then I'm gonna apply E dot dA equals Q enclosed divided by epsilon 0. One thing also I need to know that since all the points on the surface S2 are at the same distance from the center, then E is constant. Now you cannot take E out of the integral if it is not constant, all right? Okay, here I can say here, okay, surface 2, okay, surface 2, this is gonna be E dA cosine 0 equals Q enclosed divided by epsilon 0, and cosine 0 is 1, and we said E is constant. Then I can take away, outside E, and this is the integration of dA. The Q enclosed, what is really inside, if you look inside the Gaussian surface, you have the whole Q divided by epsilon 0. Okay, then this, and this is really the surface area of a sphere. And then finally, E can be calculated as Q divided 4 pi epsilon 0 r squared. Now, if you look at this expression, it's very similar to the electric field of a point charge. And when we are looking at this situation from outside, as if we have that charge concentrated at the center. One more step here I need to do is I need to say that E is going to be radially outside, and this is going to be expressed using the unit vector R. All right? Then this is really the answer to this question. Thank you, and see you soon in another video.